Okay, so welcome to the afternoon session. The first speaker will be Raghu Mahajan, continuing his lectures on black holes.
Okay. Thanks, Sumit. So I'll continue talking about the information problem. But first, I want to clear up something incorrect I said towards the end of the last lecture. Matt Hedrick had asked whether this derivation that is given in this paper of Rednan and Haag, which I presented last time, is it true for only free fields or even it's true for interacting fields? And I said that it's true for interacting fields, but it's not. Like the paper explicitly uses free field equations of motion. And one way to see where they are needed is that, so we had this horizon. There was this star falling in. We had this singularity here. There was the t equal to 0 slice. And we had some light rays that were having a very hard time coming out of the near horizon region because of the strong gravity there. And we had argued that for some time separation at infinity, these 2 points are very close to each other. So you can use some sort of UV form of a 2-point function. So that's correct. So you can, near this point, you can use the UV form of the 2-point function, even if the matter system that lives on this black hole spacetime was strongly interacting. So there's probably some power law. Let's say the UV has some fixed point, and so it's just some power law. But you still need to relate this 2-point function to a 2-point function evaluated over there. So then, basically at that point, they use essentially something equivalent to this, that if you have a free field, then even the 2-point function satisfies the wave equation, right? This is familiar from Green's functions and so on. So you can calculate this 2-point function on this time slice, but to evolve it to later times, which is what the asymptotic observer will really see, needs some kind of equation of motion. And because we have these hyperbolic equations, the light rays are relevant for that and so on and so forth. But still, it emphasizes the fact that the underlying correlations are still dictated by the near horizon physics. The only thing that the strongly coupled matter theory can do is that maybe the radiation doesn't make it out to infinity. Like, there are these gray body factors that are already present because of the potential, and maybe the interactions can like drastically modify those gray body factors such that maybe the radiation doesn't even come out, who knows. But in that paper that I referenced, they use this free field equation of motion. And once you have that, you can argue that the 2-point function has the KMS property at infinity. Okay. So that is just a correction from last time. I apologize, I misspoke. All right, so now we come to the next part, which is what happens. So we discussed the black hole that's formed from collapse, and it didn't have this influx of Hawking radiation from sky minus to stabilize it, so it was only emitting particles and not absorbing anything. So a Schwarzschild black hole, if you do the math in 4 dimensions, let's say it has initial mass m, it emits 1 quantum of energy 1 over m, so that's like the temperature scale, in a time of order m. So that means that the total evaporation time will be m cubed, because the total mass that it needs to lose is m. So roughly speaking, in a time of order m cubed, the black hole will completely disappear, and you will be just left with the radiation in flat space. Okay, so here is a paradox, because the initial state of the star that collapsed can be taken to be pure. Initial state is pure, let's say. Pure, I mean pure versus mixed. So its entropy, von Neumann entropy is 0. And as we argued, the radiation that is coming out has a thermal character. So after full evaporation, radiation seems to be in a mixed or thermal, more precisely thermal state. Okay, so no unitary operator can map pure states to mixed states. Okay, so this is the paradox that was posed by Hawking. Yes?
Even before full evaporation has happened, isn't the state already mixed from the starting? As soon as the evaporation has started?
Yes, we will come to that, and I'm slowly going to develop. Yeah, you're right, but it'll come, as you'll see. Okay, so we have some contradiction here because we believe that time evolution of any quantum system should be a unitary operator. So how is it happening here that a pure state seems to evolve into a mixed state in a time of order m cubed? Okay, so how do we diagnose purity? There are various things that pure states satisfy. So pure states for example, it satisfies rho squared equals rho, right? In particular, this means that trace of rho squared is also 1. Usually, if rho is a mixed state, it won't be 1, but for a pure state, it is 1. Or it also satisfies S of rho, which is defined as negative trace rho log rho is 0. Okay, so pure states have all these properties, and we could try to, there's one thing you could do. Okay, so these are some things. There's a harder thing you could ask for, which is, can some theory calculate? Okay, so to be mixed thermal state, so this is the state that we are calling rho here, the state after the evaporation. Calculate rho ij, where I belongs to the set 1, 2, up to e to the s. Okay, so this is the most detailed information possible about the radiation that you could ask for. You fix some simple basis, let's say some field basis or something from 1 to e to the s, and you just literally ask for all the matrix elements of the density matrix in that basis. So these are e to the 2s numbers that I think we have no hope of calculating, at least with the theories we know today. Maybe you need string theory, maybe you need strings, branes, who knows, like no one knows. So these numbers, which are traces of rho squared or trace of rho log rho, is one number. It's one aggregate number that is built out of these e to the 2s numbers. So you might hope that you have a better chance of calculating these more precisely. Okay, so here is, as was expected, I drew the entropy of this radiation or this rho state now as a function of time. So in time m cubed, the black hole is completely gone. And based on this law, you just expect the entropy of the radiation to just keep increasing linearly in time. And you start at 0 because there's no radiation to begin with. And you end up with a very large value in the end, which is comparable to the Bekenstein-Hawking entropy of the black hole. But this dot here is the assumption from unitarity. If you believe that the full evolution was unitary, then the final entropy at least has to be 0. So here, there's like a huge mismatch. Okay, so something is going wrong. But at the same time, this huge mismatch that we see at the evaporation time is perhaps not so useful because the black hole is very small at that time. It has been evaporating, it is very, very small, and its curvature is very big. So you might think that the semi-classical theory of gravity that we understand may not be sufficient to handle black holes that are so small. So in order to make progress, we can ask the question, can we push this mismatch a little bit earlier when the black hole is still big? Is there something that shows like this kind of weird contradictions, let's say at earlier times when the black hole has not fully evaporated? Yes.
You're computing the entropy for the state close to infinity, or
yes?
Okay, so why don't you expect that to be some non-zero value?
Yeah, okay. This will be covered in lectures maybe by Suvrat or Alok. I was going to explain what entropy I'm computing and say that caveat, and I will not be able to go into all the subtleties of those information localization at infinity and the constraints and all that. So we'll just make a naive split of the Hilbert space, as I'm just going to explain right now. So here I've drawn that same Eddington-Finkelstein diagram. And so what entropy are we computing? What entropy can we compute? So here there are these Cauchy slices through the space-time. This here looks time-like, but it's not really time-like. It's still space-like because in this diagram, light is not at 45 degrees. So this yellow line is a space-like slice at some time tau. And then there is a later time, the orange line, in which I have evolved forward in time. And there's another slice there. So we are just going to put this green cross here. And the black hole system is just going to be defined to be whatever state lives on this slice to the left of the X mark. And the radiation system is going to be whatever is to the right of this X point, this guy, so as a function of time. And so basically, I am assuming that if there is a matter field that lives on this slice, it has a tensor product decomposition into a subsystem which is to the left of the cross and to the right of the cross. I don't have much to say about these subtleties due to gravitational constraints and so on. Maybe we can come back to it at the end.
Your cross is at any arbitrary position or something?
Let's say at some fixed large Schwarzschild R. So you are sitting very far, not very far, maybe it's like 20 times the Schwarzschild radius.
I see.
So this could be like, I don't know, 20 m. So you just sit at like 20 m or 100 m, whatever you can pick.
Okay.
And inside that, you just declare it to be system 1.
Mm-hmm.
And outside that, you declare to be system 2.
Okay. And the line is for constant tau?
Well, over here it is constant tau, but as it comes in, it has to change. So here it's not constant tau. So far away, so far away tau is approximately equal to the Schwarzschild time t.
Oh.
So then.
I see. Okay.
Yes. Yes. So that is why I also didn't want to get into it here, but because I'm just trying to present the arguments that people have given since the 70s or whatever, 90s. Yes.
You have not quite in this diagram, you have just drawn the collapse geometry, but
yes,
you want to draw the evaporating aspect also?
Yeah. So you can imagine that this R equals 2m line is slowly moving inwards. So it is like going slowly inwards like that. So it's like slowly shrinking.
But you are still taking early time Cauchy slices or something?
No, so the evaporation is very slow.
Yeah.
So you see, it only emits a Schwarzschild quantum of 1 over m in time m, and that's a very slow process. And basically, so you can think of the black hole background as sort of changing adiabatically in some sense.
Okay.
It doesn't do much drastic things to the state. So
in that figure, we are still in early time in that sense.
Which figure?
In this axis.
Yeah, so there's early time to late time.
Yeah. So where are the slices, so to say, matching? Because
so it could, start here and go up. Maybe you can wait for some times that the transients stabilize and so on. So you could start your time at, 10 m and then go to m cubed. So let's not say that is 0. Let's say that's origin of time is like 10 times m or 20 times m. Okay, thanks for all the questions. Please keep asking them. Okay. All right, so what do we expect now? So first I'm going to give you the answer. So now let me just write the formulas. So there's a pure state psi on the system BR. You define a rho of R which is you trace over the system B of this psi, and then S rad is basically, in this definition, defined to be negative trace rho r log of rho r. All right. So let's go back here, and first I'm going to tell you the answer and then give you a expected why that should be the case. So basically what happens is that Don Page argued that, roughly speaking, the entropy should not look like this, but should actually look like this yellow, the yellow curve, something like this. So this is Page's, you can call it expectation or Page's curve or, okay. So what does this buy us? It buys us the fact that, let's say you were at this time when the black hole has only 80% evaporated. Even at that time, there is a huge mismatch between Hawking's prediction, in which you just keep emitting a thermal quantum every Schwarzschild time, and the expected answer. And the point is, at this time, the black hole is not very small, it's still very big. So this contradiction is perhaps much more amenable to a semi-classical analysis than this last one. So that is why this Page curve is kind of important and people have worried about it, because it pushed the contradiction way earlier than the final evaporation time. Okay, so is this part clear that even like when the black hole is, let's say, 60, 70, 80, yeah?
Why are you not exactly the black horizon? Describe the interior of the black hole.
Well, I just want to, because there's some, the gravitational field of a Schwarzschild black hole dies off as 1 over r. So immediately at the horizon, the gravitational field is still pretty strong. So I don't want to put the thing right there, because I want to believe that the near horizon region kind of belongs to the black hole to some extent.
That position also contains the exterior of the black hole.
Yeah, up from, let's say, 2m to 20m or something, yeah. So that is the left of the part, but here we are drawing the entropy of the region which is to the right of that X point that I drew. So that is the radiation system. I'm drawing the entropy of the radiation. So basically, let me first give you the physical intuition and then we'll discuss the mathematics. So on this curve, I'm also going to draw the area of the black hole as it shrinks. So the black hole starts out big, right? So now this is not just S rad, but also the area of the black hole. The area of the black hole is shrinking as going to 0 at time m cubed. Now, so that means that the black hole, when it gets very small, it does not have that many states, because the number of states, microstates of a black hole is e to the area at that time. And you have the second fact, which is that if you have psi as a pure state, then rho of r has to be equal to rho of b. Sorry, the S of r has to be equal to S of b. So for pure states, when you make a bipartition, the entropy of the two parts has to be equal. But if the size of your Hilbert space is not big enough, you cannot have that much entanglement. So the entanglement entropy is upper bounded by the log of the dimension of the Hilbert space. So this curve here is the log of the dimension of the black hole Hilbert space. That's shrinking, right? Because its area is shrinking. So you just know from this purity argument that the entropy could not have been this big, the von Neumann entropy, because the SB has to be equal to S of R, and SB is upper bounded by log of dB. So this curve kind of formalizes that. Okay, is that clear? There are other questions. This was an important point, so we should, yeah.
What gives me the expectation of this monotonic increase?
The orange curve?
Yeah.
That was this Hawking's calculation, which shows that this black hole is emitting one particle per unit of time, and that particle is in a thermal state. It is entangled with its partner behind the horizon, so that's why it's in a thermal state. So it's just, and each Hawking emission is independent from the previous one. So I literally have, you can just imagine like n bell pairs, and then you're just getting one partner from each bell pair each unit of time. So it's like entropies log 2, 2 log 2, 3 log 2, 4 log 2 keeps going up in time, up until the time the black hole is completely gone. So this orange curve is like, roughly speaking, you can say Hawking's curve. Yeah, people debate about the pair production picture, so I don't want to sort of really emphasize that, even though you could say that, but I'm not wanting to say those words. It is, in some sense, it is true, but let's not. Okay, are there other questions? Yeah.
What would change in this scenario if
Okay, I think I'm the post-remnant generation, so maybe someone else I think the problem with remnants, if I remember correctly, they just violate all sorts of entropy bounds that we expect from normal quantum. Maybe someone else has some comments about this.
stop at it?
Okay. All right, thanks, Suvrat. Yes.
Right?
Sorry?
As the black hole radiates, the temperature will grow.
Yeah.
And ultimately it becomes the infinity.
Right.
There is no remnants. So what about the temperature?
Well, I don't know. So that's why I don't want to be at this endpoint. That was the whole point of introducing this page curve, which is that I can just be at a very safe location. I can just say, black hole is only 70% gone. It is not that hot. It is not that small. It is just some ordinary black hole that you might be like 3 kilometers Schwarzschild radius. Like so.
I see.
So that is why you focus here, not at the end.
Okay. Okay.
This is all rough. That is why there are all these tildes and so on. It should be like there should be some differential equation, you integrate it. There will be some factor of 1/8, I don't know, lot of pi's and so on. No, it's there's this paper that I referred to here actually has a lot of plots that are more precise. So I really encourage you to look at these references. They're very instructive. So these are the original papers by Don Page in which he proposed this curve. This is a later paper which was trying to make these curves more precise. And this is a proof of something that I will say later. Okay, so let's try to give at least an intuitive a calculation which I think is very instructive, at least to me, about how this kind of a curve arises. So we are not now going to not talk about black holes for maybe the next 10 minutes, but this will be instructive. So let's say we just have a state psi br, which is equal to some coefficients cbr times b on the system B, R on the system R, and there's a sum B goes from 1 to dB and R goes from 1 to dr. Okay, so B and R are two quantum systems. The total Hilbert space is a product of them. And then we just have this state. dB and dr are two numbers that are the dimensions of the system B and R. And what we will do is we'll take CBR to be IID complex Gaussians. With a mean 0 and expectation value of CBR squared equals dB times dr. 1 over. So that this state is normalized on average. So it's not always normalized, but because you are picking these to be some random variables, but on average, this state is normalized if you pick this variance. Okay, so now we just calculate rho r. Rho r is trace over B, psi, which is C BR C star B R prime, R prime. Okay, all indices are summed. So this is a state of the R system. Then we can compute rho R squared, B C B R, C star B R prime, C B tilde R prime, C star B tilde R double prime, R double prime. Okay, so this B index is already contracted. So this is a matrix element rho R prime. This is the matrix element rho R prime R double prime, and then the column index here and the row index here get summed. So this is the matrix rho squared. And then we can calculate trace of rho R squared, basically C B R, C star B R prime, C B tilde R prime, C star B tilde R. Okay, and summed over B tilde R prime. Okay, so now these are Gaussians, so we can just take the expected value of trace rho squared. Because it's Gaussian, there's a Wick's theorem. So there are two contractions where we have 1, 2 contracting with 3, 4, or we can have 1 contracting with 4 and 2 contracting with 3. So the yellow contraction gives us what? So this one here will produce a delta of R prime, and this B index will just get summed over. So I'm going to first write the yellow result. So there will be an overall 1 over dB square dr square, just from, because we have 2 of these contractions. And then the yellow one gives dB delta R prime, dB delta R prime, and then the orange one is dr delta B tilde, dr delta B tilde, and now you perform the remaining sum over R and R prime. So you get 1 over dB square dr squared, dB squared dr plus dr squared dB, which is 1 over dB plus 1 over dr. And it's equal to 1 over dB if, let me write it in the order I have it in my notebook. It's equal to 1 over dr when the B system is very large, and 1 over dB if R is much larger. Okay, is this calculation clear? Are there any questions about the contractions and so on?
Dr arises in the second line because the first line is dB times dB times delta, right?
Yes.
So how you get the dB square dr?
Because you're still summing over R and R prime. So it's a double sum, but because of the Kronecker deltas, it's just a single sum.
Oh, I see. Okay.
So it's like a single sum over R that gives you this dr.
Okay, the number of Hilbert space dimension. Okay.
Sorry?
No, it's okay. Yeah.
Yes. So you see, first of all, it's symmetric between B and R, like we had argued that for bipartite pure states, that this. And here you see B here is a much larger system, so R is much smaller. And when does the trace rho square equals 1 over dimension of the Hilbert space? It's when the density matrix is fully mixed, right? So imagine a density matrix rho R, which was fully mixed. That would be 1 over dr, 1 over dr, all the way 1 over dr. So when you take trace rho R squared, you would just get 1 over dr, right? So this is what this is saying. It is saying that if you have one very small system, R, and one very big system, B, the state on R is fully mixed. Like there's just no structure in that state. And similarly, the other way around. Okay. So this now almost justifies that curve, because it's just saying that if the state of this black hole radiation system was kind of typical, like, so, these are random numbers. So imagine that as the black hole is evaporating, the state that it's creating is very complex. So it almost looks like some random state. Then we expect that the entropy should follow this kind of a law, that the smaller subsystem is fully mixed, and that's it. So that dictates that curve. So before the halfway evaporation point, this kink, the radiation system is smaller because the black hole is very big. The radiation has just started coming out. So the radiation system is fully mixed. And after the halfway point, the black hole is now smaller. So its entropy is dictating the von Neumann entropy across the bipartition. So that kind of explains this curve. Yeah. For the random state case, yes, it will be linear. Like if you take that model, let's say you could even improve that model and just not take those Gaussians, but really take a random state on the sphere in Hilbert space.
That argument is an argument about the sizes of the Hilbert space.
Yes, yes. Okay, good, yeah. So what is happening here? So something similar is happening here, because the black hole is not just emitting particles and entropy, it's also losing energy. So you can imagine that as the black hole is reducing its energy, this area was decreasing, right? So the dimension of the Hilbert space is decreasing in some sense. The dimension of the Hilbert space available to the microstates of the black hole is getting smaller as time goes on. So because there's also some energy transfer happening. And actually, that point, I want to mention this really nice work by people at ICTS, Manas Kulkarni, Abhishek Dhar, and Madhumita Saha from earlier this year, where they just considered a condensed matter system. It's like some free fermions that are hopping on a line. They're filled up to some point and then it's empty. So it's like a box of gas which expands into a vacuum. And they can make all these notions precise. Like there's like a system, there's a reservoir, and they can basically, there's some hydrodynamic notion of the radiation entropy, which follows this orange type curve. So they have some hydrodynamic approach to solving the system. So some kind of coarse grain entropy keeps growing with time, whereas the actual von Neumann entropy turns over. So you can see this in like just basically this phenomenon has nothing to do with gravity, like these curves. So I encourage you to look at this paper. And there's literally a plot where there's some hydrodynamic entropy of the reservoir that shoots above this tent type curve. Yes.
What happens with the dimensions of the Hilbert spaces as the black hole evaporates? Is there some constant?
So the black hole Hilbert space is shrinking and the radiation Hilbert space is growing.
Is the sum of the two dimensions constant?
The product roughly is constant. The number of, like the total energy in the system is constant, so you can think that way. Yes.
Over here, is dB in the fixed forever?
Yes.
But so when R is much larger,
Yeah.
if you try to compare it with this, the black hole Hilbert space is decreasing in size, right?
Right. I think as she was asking, you can imagine that dB times dr is fixed as a function of time. So this is for any dB and dr. And as time goes on, dB of t decreases and dr of t increases.
So the product is fixed.
Yes.
So that means this says that this quantity is growing larger and larger as R is getting much larger. Is that correct?
So what? Can you say that again?
Because dB is getting smaller, 1 by dB should get larger, right?
Yes.
And that is happening in the second half.
Yes.
Associated with radiation entropy going down.
Oh, sorry. There's a log here that I haven't written. So this is just trace rho squared. So to compare to the entropy, you should compute the second Renyi entropy. which is negative log of trace rho squared. So I forgot to say this, yeah. So that will fix that. Yeah. Yeah. Yes, yes, yes. Yeah, yeah. Yeah, but this is the thing that you typically assume when you have large Hilbert spaces and law of large numbers, that if you had one state which is typical, then that will try to follow the average behavior of the system. So I cannot defend this assumption more than just saying that you might hope that an actual black hole that evaporates, its state is so complicated in terms of some simple basis that the entropy of that state does indeed look like that of a random state. So this assumption is made in a lot of works on this black hole information problem. Like you use properties of random states to make guesses about what complicated individual states might do. So. Oh, exponentially.
Most states are not black holes.
Oh, yeah, yeah. Okay.
So is that the concern that you're worried about? That most states would not be black holes, therefore maybe this is not black holes don't behave like typical states.
Well, I was just responding to his question about why I expect this curve, even though the black hole state is an individual state versus this is a computation about some average.
Right, right. But in ADS-CFT, even though black hole state is an individual state, most individual states do behave like typical states.
Okay, yeah.
Maybe in flat space, we would be concerned that
Yeah.
most individual states are not black.
I agree. So then we could work with the small ADS black hole, which is somehow evaporating, and plot, define somehow its radiation subsystem and black hole and work with it. Yeah. Okay. Point taken. Yeah. Well, the space-time part behind the horizon ends kind of. There is still flat space everywhere. Yes. No, the time evolution should be unitary throughout. Point is, at the end, the black hole. Yes. So are you saying there are some baby universes or something that are get emitted or? Yeah. Yes.
And they showed that the full quantum reacted spacetime, backreacted spacetime, the scry is genuinely larger than scry of the classical. So then it turns out that you have like small circular corrections to your Hawking radiation, and there is enough time for them to purify. I mean, I'm just saying there was one scenario that.
Okay, I'm not aware of this scry plus being larger or something. Maybe we can talk about it. My understanding of the CGHS model, at least the papers I know, there was this paper by Fiola, Preskill, Strominger, and Sandip Trivedi, in which they tried to calculate some von Neumann entropy of Hawking radiation, and because they didn't have these extra saddles that I will eventually talk about, they just got some linear curve like this. Yeah. But I don't know about the Ashtekar work. Okay. I know that people did the numerical simulations, but this part I was not. Okay, great. So let's move on. So now we have discussed this page curve, and there's a contradiction even when the black hole is very big. So now we come to how to set up this problem in ADS-CFT. So has this Liukovitz-Maldacena paper been discussed at all right now in the lectures, till now in the lectures? Not yet? Okay. So that is the thing we will discuss next, because now we want to go towards the theory of quantum gravity or semi-classical gravity that we think we understand a bit better, which is ADS-CFT. And in ADS-CFT, there are certain prescriptions to calculate the entanglement entropies, of von Neumann entropies. Ryu-Takayanagi formula and its proof by Leukovitz and Maldacena. So that's what we will talk about now. So in order to really see how we can improve upon this curve, if at all we can. No, this is, if you look at these papers, they already have corrections to this. So there are some corrections in dB divided by dr. So it's actually rounded up. But yeah, if dB and dr are very big, like naively, it looks like a first order phase transition. In gravity, typically it is a first order phase transition, unless you are very precise about that being. Okay. All right, so now we talk about okay, so the first thing that is done is to, note the following equality. Okay, and then instead of considering things like trace rho log rho, you consider trace rho to the n. So this is like a generalization of that trace rho square for arbitrary n. And you hope that even though you start with integer n's, you can analytically continue to complex n, in particular to n equals 1 plus epsilon, and then read off the entanglement entropy from the piece, which is linear in epsilon. So this is called the replica trick, and I believe Matt covered the replica trick for just QFT, right? Okay, so rho for us will always, I emphasize this, be a state of maybe a subregion of the boundary quantum system. So you could think about SYK model, n equal to 4 super Yang-Mills, whatever. In particular, this boundary quantum system has no gravity. Okay, so that's what we want to compute. We want to compute entropies in a completely non-gravitational system. I emphasize this because there are many papers that try to, like even maybe till now, do the replica trick in the bulk. And if you interpret those correctly, they maybe give you some answers, but that's not the right perspective. So you're really supposed to do the replica trick on the boundary. Okay, so you set up the boundary replica manifold. And you basically want to compute the Z, the partition function of the QFT on this particular replica n manifold that computes for you this trace rho to the n. Okay, so then we use the fact that trace rho to the n using ADS CFT is equal to e to the power minus I1 star plus e to the negative I2 star plus e to the minus I3 star, blah, blah, blah. Where I1 star, etc. are on shell actions of ADS type, asymptotically ADS saddle points to the bulk equations of motions with the replica boundary conditions. Conditions at infinity of ADS. Okay, whatever, yeah. Okay, so this conceptual point has to be completely clear. So please ask if there are any questions about this, the ADS-CFT method of computing this quantity. Okay, and one important point that was, yes. There could be, well, yeah, let's say I work with Euclidean signature to simplify things. Typically they're complex, so they could be anything like Lorentzian, complex, or Euclidean. In the simplest cases they're Euclidean, so I have put minus sign here. And the point is there could be multiple of these saddle points. Not just one, but there could be multiple. And the punchline is going to be that this tent type curve comes from an exchange of two of these saddle points. So at early times, there is one kind of saddle point that contributes, that gives the linear in time increase. And at late times, there's a different saddle point that contributes because its action is lower. So that gives the falling down part of the curve. So, and there's a first order phase transition. There's an exchange of saddle points, and there's a first order phase transition. So this thing is sharp. Yeah. Yeah.
The bulk doesn't develop something strange.
No. So I think this is the main point, actually the conceptual point in this paper is that you can have completely smooth bulk manifolds with these replica manifold boundary conditions. So you should not allow any conical deficit, singularity, or anything in the bulk. It's just like Gibbons-Hawking. You set up some beta boundary condition at infinity, and you ask, what are the smooth cigars that fill it in? And there's a particular cigar with a particular value of R plus, the horizon radius, that will fit a given beta correctly. So that's the kind of thing that goes on here. No, in principle, no. But for n not close to 1, finding these saddle points is extremely complicated. So in practice, yes, you always work near n equals 1 and so on, but in principle, n could be arbitrary. Yeah.
It should be right-hand side.
Yeah.
It should be evaluated at the the boundary at z equals to epsilon or some.
Well, no. So this thing, so this is a bulk on-shell action. It will be an integral over 5-dimensional ADS, let's say if you're in ADS 5. It's not just some boundary thing.
Okay, we have not to take any limit on the z in Euclidean signature, let's say, or it's a
No, see,
bulk.
when you compute the on-shell action of a geometry, it's a GR action. So if you have a 5D ADS, the action will be integral d5x plus maybe some boundary term.
Yeah.
But typically there will be a bulk contribution and maybe some boundary contribution, and you have to add them together.
Okay.
For each I1 star, I2 star, I3 star.
Yeah. Right. Okay.
Okay. Yes.
In LHS and RHS, that time of the
This rho is a function of time. The density matrix of the radiation. So we will eventually be interested in computing this quantity where rho is the density matrix of the radiation system. And the state of the radiation for an evaporating black hole, actually in some cases even as I will show, even in an eternal black hole, is a function of time. So it's basically rho can be a function of time. And then for each of those times, you have to do this thing again and again and again. So these saddle points will depend on that because the input to the boundary condition is depending on time. Okay. Yes, I'm like going very slowly. So. All right, so the upshot of all this.
One question.
Yes.
In the left-hand side, the n appears, but the right-hand side, how? I mean, what is the signature for that n? I mean,
Here.
no, in the left-hand side, n is there.
Yeah, on the right, you're asking where is n on the right-hand side, right?
Yes, yes.
It's here with the replica boundary conditions. So this replica boundary condition depends on n.
I see.
Right? So the n enters through the boundary condition.
Okay.
So and it's very important. So that's why it's very important to have these saddle points to have the right boundary conditions.
I see.
Like always, like any quantity in gravity that you compute has to enter through some boundary condition.
Right, right.
Yes.
Not about the
Yeah.
the Maroc-Max field generalization.
Okay.
So there, it was a Lorentzian.
Yes.
But is there an analog of the replica boundary? I was just, I don't know.
Maybe can we talk about this later? So this maybe is not directly. Okay. So what is the upshot? So this is the conceptual input, the output of this process, and this is a lot of hindsight that I'm using. There are papers by Faulkner, Lukowitz, and Maldacena, and then various other people that put in a lot of work into this, including a very nice paper by Engelhardt and Wall, and then culminating in this work of Pennington and Almehri, Engelhardt, Merolf, and Maxfield, and then the replica of So those references you probably all know or can look up from various talks. But here is the output. The output is that in many but not all interesting setups, the output of this is the following. The S of this boundary system, of the boundary region that we have picked, equals minimum over bulk regions that are deformable to the boundary, region, if I write here, is probably not visible, right? So let me put here the quantity that you're supposed to minimize. A over 4G plus the entropy of bulk matter in this region. Okay, I'll draw a picture so it'll become clear. Yes. It's an approximation because it's a saddle point approximation. In principle, you could compute both things exactly. Yeah, so we are working in the G Newton equal to 0 limit, or G Newton being very small. So we are just want to compute the entropy to leading order in n square. Otherwise, there'll be loop corrections and so on and all these things. Okay, so what do I mean by this thing? It becomes clear with a figure. So let's just draw ADS3. You have some spatial slice, and let's say you have a boundary subregion, which is this arc here. Then candidate bulk regions over which you should minimize are these sort of yellow regions. Okay, so the union of these three is a particular bulk region that you could consider. And the only restriction on these regions is that they should be deformable to the boundary region. So these things in the middle are just deformable to nothing. You can just squish them completely away. And then this region you can deform to the orange part, right? So there should be a deformation retract of the bulk region to the boundary region. So that's the only restriction. And importantly, these disconnected regions can sometimes be important. So those are called islands. So if the minima minimal region includes disconnected parts. And these things are called islands. Okay, that's the definition. Now, you might worry, why should you ever want to include such a thing? Because after all, in the minimization, there's an area term present. And clearly, if I deleted this region, I would save on the area cost because I'm paying, by including this bulk region, I'm paying a cost which is proportional to the area of the boundary. But the point is there's a second term there. And the second term is just the entropy of the bulk matter fields. So the bulk matter fields in the yellow region will be entangled with their complement. And that has some entropy, right? So the bulk field just restricted to the yellow region have an entropy, and that's the second term. So sometimes you can save by including these regions because you pay a cost which is proportional to the area, but it might be that the particles in this region were very highly entangled with the particles in this region. So then when you include both of them, the Bell entanglement does not show up in that extremization quantity between them. I don't know of explicit examples, but I'm sure we can cook up some scenarios where this kind of a thing can happen. I don't know of any no-go theorem that would prevent this kind of thing. Well, I have not come to the bath yet. I'm just presenting the structure of how entanglement calculations should be done in ADS-CFT. Yeah. If the bulk state is kind of complicated and messed up and I have arranged things such that like particles here are really, really entangled with particles here, I don't see, or at least let me not say, I don't know of like an actual calculation that people have done, but I also don't know of any no-go theorems that would prevent entanglement wedges that look like this.
I think there would be a problem. I mean, maybe theoretically there's no no-go theorem.
Yeah.
There's potentially a problem, right? Because operators there have nowhere to go. And this theory is not a massive theory. Here gravity is not massive because there's no bar. There would potentially be a problem because operators in the middle of the island would have nowhere to go. And I think you're right, it's not a no-go theorem because things are sufficiently dynamical and so on.
But again, I'm making statements that are referencing maybe just a particular semi-classical background. So then I can just like pick coordinates and this thing is diffeomorphism invariant. There is no problem with constraints or anything. I can just fix once and for all some coordinates on some background. Yeah, then just that is well defined.
I think there would be a problem because an operator in the middle of the island wouldn't commute with the Gaussian surface that surrounds the island. Even if you could make it differentiated, because you make a Gaussian surface around the island.
Yeah.
You would find there's a non-zero commutator because if you insert mass in the island,
Yeah.
you create a gravitational field.
But the Gauss law is the mass is measured at infinity, right? And my infinity is not included all of it in this thing.
Yes, but there's also a Gauss law for regions like we think there is, right? Which is you should be able to measure the mass inside a finite region quasi-local way by surrounding it with the Gauss. So you're right, it's not a sharp objection because that's not a positive definite quantity.
Yeah.
So you might say that there is no quasi-local energy or the energy
Yes.
is infinity. But I suspect that's the reason such islands have never been found. Like we don't have.
Well, okay, I think at least the kind of arguments you have about Gauss law at infinity don't apply in this case. And then this more refined argument of surrounding it locally, I don't know, maybe we can discuss it later. Yeah. Well, so that bound literally is not true for just space-like regions, because that can be violated. Like we can definitely, if you just have a space-like slice with some area, then I can just have scenarios where there's arbitrary amount of entropy inside of it.
Even if you don't have black holes surrounding it?
I don't know. Yeah, if you don't have,
Yeah,
Yeah,
in
now
this
I
case,
know
there is no
example of a
horizon.
black hole. I know examples of collapsing black holes in which that.
Yeah, they are actually, I think it's true.
Yeah.
But in this case, you don't have any horizon or anything, right? Just an ordinary region.
Yeah. So that's
you are
the
trying to
figure I
form.
drew, but I meant like in a completely general setting.
I see. Okay.
One should allow these kind of things
Okay,
and
yeah.
then check if such a thing exists.
Okay.
And of course, the applications we know are in the black hole evaporation
Yeah.
process and so
Okay.
on. So, but I think it's an interesting question. I don't know. Maybe some people who are more familiar with the work of Akers and Pennington have some more things to say about this. I have not really kept up with all the details after a certain time in the past. Yeah, that's the thing I had in mind, but. Okay, fair point. But such things will come up when we consider evaporating black holes. So anyway, so I want to just summarize the setup again. So you always start with a state on the boundary whose entropy you want to compute. You set up the replica trick with this integer n boundary condition. And then you use ADS-CFT to fill in the bulk with smooth saddle points. There might be many of them. And interesting cases which people discovered in 2019 were when there are multiple saddle points, contributing in the case of evaporating black hole. Multiple saddle points, of course, are known in the case of, for example, just mutual information in ADS3 of two regions. Different RT surfaces can compete with each other. Yeah.
If I was not thinking of the left-hand side, something to do with the CFT or some field theory.
Yeah.
But just as a gravitational calculation.
The left-hand side?
Yeah.
This?
Okay. Let's say the path integral, whose answer is the right-hand side.
Yes.
I just think of it as the path integral of gravity with those boundary conditions put on somewhere.
Yes.
Suppose it's not even asymptotically ADS.
Okay.
If it was not asymptotically ADS, you wouldn't be able to relate this to some field theory, I understand.
Mm-hmm.
But is there a statement about that? Maybe if I take a replicated region somewhere in the bulk, just like that, if the cylinder is not at the Pawel boundary.
Mm-hmm. Yeah, I don't know. If I think
some people claim it is also and Pennington.
Yeah, I haven't really kept track of the recent work. Like they have some work about defining entanglement wedges for regions that are deep in the bulk. I just haven't followed it that closely. Maybe other people in the audience have. But let's discuss that afterwards. I want to continue. Okay. Okay, all right. So today I'm just like doing very different topics, but so the actual calculations that I'm now going to describe are in this paper that I wrote with Ahmed Almeri and Juan in 2019. So I will only be discussing the setup in this paper. But the particular model of time evolution that we used was not this evaporating black hole because the model is a bit simpler. And that model of time evolution was first discussed in these two papers by Hartman and Maldacena and a paper by Samir Mathur in 2014. Okay, so what is the setup? The setup is you consider the thermophile double state, e to the minus beta en over 2 n n. So let's call this psi. There's a sum over n. So now I have in mind some eternal, just a thermal state of any system which is purified into a thermophile double state. And the model of time evolution is just e to the minus it. First, let's consider this h right minus h left. On psi, it will just give psi back. Just because the energies are equal, so when you just get a phase factor, you get En minus En, and you just get psi. But you could also consider e to the minus h it, h right plus h left on psi, and that's some non-trivial state. So this is some function of time. Okay, and because the state psi is not any close to any eigenstate or anything of h right plus h left, you typically expect that entropies of subregions in this state will grow linearly in time. So because psi is like a quench state from the point of view of the Hamiltonian h right plus h left. Okay, so here is what we are going to do. So, yes.
Raghu, is this obvious what you said?
It's not obvious. So let me say are expected to grow. You expect because you see, let's say imagine the following situation. Let's say we have some complicated Hamiltonian, and I just prepare a product state of all spins up. Then under time evolution by that Hamiltonian, typically like the entropy of some region grows linearly in time. And there are various models for this. Like there is this quasi-particle free streaming model in integrable models. And in more sort of these chaotic models, like which you could model maybe by Brownian systems, there is this membrane picture of entanglement growth. So there are various arguments for this linear growth, and it does happen. Like in ADS-CFT, in this Hartman-Maldacena paper, you see it explicitly happening. Could be either. Could be, well, if it's only on one side, then it will not evolve.
Yeah, because you can do it on the other side.
So it has to be a subregion, which they picked was a subregion on the left and a corresponding subregion on the right.
I see. Okay.
So let's draw. So here is the setup. So we are going to be in 2D gravity. So let's say I denote here this SYK model that was being discussed in the previous lecture. So this is a system with n fermions, and we just consider that system for now. It's dual to some two-dimensional theory of gravity, but it's like there is no local structure within it. So you should think of this as like a point which has some n fermions in it. And because this thing in its thermal state will be dual to an ADS black hole, and ADS black holes are eternal, which will not evaporate. So what you want the setup to be is that this thing should be coupled to some kind of other chain of fermions. Okay. So this is a bit like the setup also in that 2402 paper by the ICTS group, where you consider some system which is interesting for you, and then you let its energy leak into some environment or some bath. Okay, or reservoir, whatever we want to call it. And now we put this whole thing, so there's some coupling between them. We put this whole thing in the thermal state. Okay, so this combined system is in a thermal state at, let's say, temperature beta. Okay, so every thermal system admits a purification. So its purification will be involved. So now I'm going to just draw this as a line. Will involve a second copy of both the systems, like that. Yes. So I mean, here nothing is gravitational. Here is just SYK coupled to wire. So here there is nothing gravitational. And as I was saying, the entropy, the region whose entropy we are going to compute is going to be defined on the boundary. So this is the boundary system now, or whatever, the non-gravitational description. And the radiation region is going to be this so-called yellow region. So I'm just going to call this faraway region to be the union of these two is radiation. So the radiation system is the union of the two yellow regions. And we are going to just call this coordinate 0, and this will be B, and this direction will be Y. Okay, and now we have a thermophile double state. So this whole thing is in a thermophile double state. So this system is purifying that one. And now we apply this Hamiltonian to this state. So there is a left system combined and a right system combined. And we essentially do this time evolution and ask for the entropy of this yellow region as a function of time. Okay. So again, like naively, what do we expect? We expect, because of the arguments we just discussed, that the entropy will grow linearly in time. But let's think of the complement of this yellow region. The complement of the yellow region is just 2n fermions, n here, n here. So at max, the entropy can be 2n times log 2. So at some time of order n, the entropy has to saturate. So that means that the entropy as a function of time should look something like linear and then flat. So here we don't have some tent coming down because we are in this special setup, which is this non-evaporating black hole, and we have this time evolution. But essentially this phase transition, this sharp transition, you should again think of as being due to, in the gravity calculation, there will be two different saddle points. One which will give this answer, and after some point of time of order n, it will become subleading, and then this some other saddle point will give you the right answer. So this is the relevant page curve for this setup. And we just study this because it has all the essential physics, at least from the point of view of losing the evaporation part. Evaporating black holes are complicated, the metric is complicated. It doesn't get around the fact that you have to have this bath and so on, but still. So this is the thing we want to calculate, this curve. Okay, are there any questions about the setup? Yes. So this state psi now is a state on 4 systems. But we sort of think of this as left and this as right. Yeah. Yeah, so you will basically, you will have n copies. So this is your full system. So you'll have n copies, and you will trace out the, like Matt explained in the QFT, essentially it will be the same. So you'll trace over part of the thing and connect the radiation parts in the cyclic order and so on and so forth. So the bulk we'll come to. So right now we haven't discussed the bulk. Well, in the bulk, let me tell you, I probably won't have that much time. It's 10 minutes. But I'm not going to go through the whole replica setup. We are going to use in the end, just for the purposes of these lectures, just this rule here. So we are just going to consider candidate surfaces and extremize over them. The replica manifold, I used it as a motivation to get to this final answer, and it's conceptually very important to always remember this. But in this particular setup, we'll just use these formulas and see how that curve is reproduced. So I'm not actually going to do the replica calculations. Yeah.
Of order n, has the system come to equilibrium?
Has the system come to equilibrium? Under this time evolution, you mean? So from this observables point of view, yeah, you can say that the entropy has saturated. But there might be other observables that keep evolving in time. So, in terms of? In terms of the bulk. Well, so this is the thing, right? So the entropies can saturate very quickly, relatively quickly. For example, if I just take some system size of order 1 and the entropy grows linearly, it will quickly saturate. But that doesn't mean that other interesting observables are also saturating at the same time. So like, for example, the 2-point function or some 4-point function will continue to change as a function of this time. So you see the state, underlying state is a very complicated object. It is a state in a very big dimensional Hilbert space. Here we are just plotting one number, built out of that state. So there might be other, of course, these coefficients continue to evolve. Eventually there will be some recurrence and so on and so forth. So you could say that it has reached some kind of equilibrium from the point of view of entropy. But yeah. Yeah.
But then in the case of black hole, if you want to think like this, then we will go into this
AMPS type of problem. Well, radiation is the bath in some sense here. So what will happen is that you have some, thermal state set up here. So first of all, this setup is not evaporating. So, but the point is here I have defined the radiation system for you. The radiation system is a subsystem of what I call this reservoir. You could then debate the physicality of the setup and so on and so forth, and I'm willing to do that. But this is the definition. This thing is the bath, and I have defined this to be the radiation. B could be 0, doesn't matter. B could be very small. B is not going to be very important. Sorry, yeah. You have a question?
No, I'm saying that I thought that.
Okay. Is the island.
I mean, the radiation will describe some degrees of freedom.
Eventually. Yes.
So that's how the PLP is kind of.
Okay. Yeah. Yeah. Question.
How do you couple
It could be very simple coupling, like you could take each fermion here, like it could be something like some, so let's say there's also some fermionic creation operators here. So you could just make the fermion hop. You could take the SYK fermion and just make it hop to this, let's call this fermion operator C0, to C0 dagger or something like that, just some coupling like this. No, if it is strong enough and its system is thermalizing, it will not. So this paper, that's why this paper from 2402 is nice, because it explicitly has some model of this coupling and still gets all these curves nicely. If it's arbitrarily weak coupling, then yeah, you will have to wait a lot of time before things can build up and so on. So numerically, that's the advantage, that you can take the coupling of order 1 and go with that.
I think this is much more complicated than what you are making out.
Okay.
We have investigated this problem, right?
Okay.
Of coupling the SYK model to the bath. And the coupling depends on what type of coupling you take. In some cases, the black hole evaporates into a smaller one. In other cases, it evaporates completely evaporates.
Okay. So sometimes the evaporation stops.
Yes.
I see.
So I think this is a very complicated problem, and in fact, we have written a couple of papers.
I see.
Gautam Mandal, Anurag Kaushal, and myself on this problem.
Okay.
Yeah.
Okay. Thanks for the comment. I was not aware of this stopping of the evaporation. All right. How much time do I have? 5 minutes. Okay, I think I basically now have to get into the dual of SYK, which is JT gravity, and entanglement entropies in CFT2, which is like a whole different topic. So maybe let's just stop here and have maybe a few more questions. Yeah.
So I know it's getting a little bit ahead, but since your computation on the gravity side is going to be all Euclidean, some Euclidean saddle points, how can you possibly ever get some information about what happens behind the horizon? You cut it away.
Well, they're not always Euclidean, they're generally complex. That's the first comment. So we should not dismiss Euclidean or complex saddle points right away. And as I emphasized, we should not try to calculate everything all at once. All we are trying to calculate is one number, it's S rad of t. And that's it, like that's all that I'm going to talk about. You could talk about entanglement, wedge reconstruction and all those kinds of things, but one of the lessons that I seem to have taken away from all this discussion is that at the end of the day in a physics calculation, you're always computing a number. So this is the number we are computing, you set up the boundary conditions appropriate to that, and you get some curve and you just interpret it. And I don't know if it has information behind the horizon or not, but it definitely has this plateau that will kick in. So one could discuss these more slightly less defined questions about operator reconstruction and things like that, but at least it should be clear that what calculation we are doing and what number we are computing. And I think it is also not true that Euclidean calculations never know about Lorentzian physics. Classic example of this is just tunneling, right? Like in quantum mechanics. You can do a purely Euclidean calculation of an instanton. You get some tunneling rate. There is Lorentzian physics in it, which is that if you could take the wave function of the particle and evolve it, you would see the tunneling rate even in Lorentzian physics. So, it depends on the case that you're studying. It depends on the problem you're studying. Yeah. Yeah.
We just have like one energy and n, or you there's some summation convention?
Sorry. I'm summing over n. And there's also 1 over square root of z. So sorry.
But do you, if for example, if I take one energy, or like some sum of the energies up to some cutoff, do you expect similar behavior?
In the model, I don't know how to answer that because we really use the thermophile double geometry, the full geometry. So in that sense, we are restricted to this state. But if you do some modifications, then I'm not sure. Yeah. Yeah. Yes. Yes. Yeah.
So that in some regime there was a holographic distribution, in some regime there was.
Yeah.
Then in the holographic regime you'd be able to compute it using.
Yes.
But then we tune the parameter, the boundary result should still be true.
Yeah.
So the holographic computation will somehow see.
Yes.
So there's some understanding of how that might happen, or is that a useful kind of.
Okay, so just to understand the question, we could ask this question about any observable in ADS-CFT, not just entropy. Yeah.
And then you get from strong to decoupling.
Yeah.
Even at decoupling, I expect a phase.
Yes. Yes.
But the holographic calculation is valid at strong coupling.
Yeah.
It's like some protected quantity almost, the phase coupling. It's not protected by theorems, it's protected by genericity.
Yeah.
So there's a parameter you can.
Then there are other quantities like this. For example, this ramp in the spectral form factor is similar.
Right.
So if you're at strong coupling, but it's like saying, it's only at strong coupling that a black hole gives you the entropy of n equal to 4 superyoungles. If you go to weak coupling, you will have some entropy as a function of beta, but you will not be able to calculate it using the horizon of any black hole. So that's basically the same. So, you know. So at some point when you make the coupling weak or n small, the bulk analysis ceases to valid, but that's true for almost anything we can compute, like entropy or this form factor. Yeah, right. Yeah, so the ramp is computed by this double cone, but the double cone only makes sense for holographic theories. Any other question? Yeah.
About the island.
Yeah.
So the disconnected regions should consider only if they have some entanglement with the surface we can deform to boundary. Or?
Yeah.
Otherwise, we have not to consider.
Yeah, like otherwise it's very hard, right? Because the first term, the area has a 1 over g, and the g is usually very small.
Okay.
That term is usually very big, and like was anticipated. You really need some contrived setups for these things to exist. And sort of the evaporating black hole, or this kind of phenomena for late times, builds up that amount of entanglement between some disconnect. We'll see in the next lecture how it happens.
Okay.
Yeah.
In the schematic picture of islands you showed, like there were some complaints raised, right? Would any of them be like better if you have the islands connected to the main entangled wedge? Or is there a
Sorry, I missed part of your question. Could you say it again?
These disconnected islands you schematically drew there.
Yes.
And the objections which were raised around it.
Yes.
Would it be better if you have the islands anchored to the anchored island, like by maybe thin lines or something, like, or is there a reason you didn't? Yeah, but like maybe islands but connected with some bridges or something. I mean.
Then it's just one continuous surface, right? Then
is there a reason you didn't prefer these, or like?
But that I just included. That's like a no island case.
But you would still have these extra contributions, and I would assume the bridges don't contribute much or something, no?
But I would count that in the RT surface already, right? Like, so even though there's a narrow bridge, it is still connected, right? So I was just making a distinction between connected versus disconnected.
Okay.
Of course, you could have this bridge and something, nothing prevents you from that, but the topological distinction is sharp between a connected thing and a disconnected thing, right?
But you would still gain the advantage you'd gain by adding those islands to cancel. And
but then if in the bridge there is not much entanglement, then you're just adding the area of that bridge part, right?
Which would be very narrow if you, I don't know, I'm just guessing. Like.
But it's still something non-zero, right?
Sure, thanks.
It won't be extremal in particular, like the bridge will want to pinch off. The point is, we shouldn't just calculate this A over 4G plus S for any surface. You also first have to minimize this. So that means some derivative has to be 0 first, and then you should look at all the things. So if you have something like that, it will just not have a 0 derivative. It will just want to shrink.
Because you could anchor operators in the bubbles to the boundary and that kind of stuff,
Okay.
Yeah.
But there's a question there, yes. Yeah. It is, yeah, semi-infinite, yeah. Well, the reason was this figure that I drew here. So in, a black hole, there was this X point, and something to the left of the X was sort of strong in the strong gravity region was called the black hole part of the slice. And then everything to the left was sort of flat space where the radiation eventually ends up. And, sorry? Oh. Well, then it's not a purification of some system, right? So I wanted to first think of it as this system, which is semi-infinite, and then this is just a purification of this. So I don't know what it would mean to have some periodic boundary condition here. Oh, you mean this back to here? Oh yeah, so that does not mimic flat space, right? Like in asymptotically flat space, radiation moves out to infinity, goes to Scri plus, doesn't suddenly appear at r equal to 0, right? Okay. Was a question here? Well, it's deformable because these disconnected regions are deformable to nothing, right? They are like you just shrink them to a point and it just disappears. This part has to be deformed to the boundary. So all the yellow lines you can deform away, basically. You cannot change the boundary anchors, but if it's purely in the bulk, you can deform it. Yeah. Yes, yes, yes.
Otherwise, you would just get the working kind of.
Well,
The page kind of.
yeah. So if, there was, so here I took thermal equilibrium, right? There's a finite temperature system coupled to a bath. So you see, it is here. So this system is coupled to this, the Hamiltonian is coupled. But together I have taken it to be in a thermal equilibrium state. If I had done something like a quench, like Spenta was saying, where you take a finite temperature SYK state and then at T equal to 0 join it with a wire. And then the initial state is not a stationary state under that Hamiltonian. And then it would be more like an evaporating black hole. And that was actually also the case considered by Almehri, Engelhardt, Merolf, and Maxfield in their first paper. There, this thing was at finite temperature, but this was at 0 temperature, and then they were suddenly joined. But because this system is infinite, almost all of the energy here leaks out to this infinite bath. So this thing cools down to 0 temperature, starting from 0 temperature, and the whole thing sort of comes to a 0 temperature final state. So then you have the tent.
If there are no other questions, let's thank the speaker again.
Thanks.